Hi, this is Rebecca Farrington from the University of Melbourne. Today I'll be presenting on the destructive tendencies of cratons. It's a 3D geodynamic modelling study of cratons and subduction. This work is done in collaboration with Katie Cooper at Washington State University in the US and Meghan Miller at ANU. So I'll quickly discuss this image I have on the page. You can see that we're looking at the Caribbean plate and the Amazonian craton, as well as the Antilles subduction zone. So the red lines there at the Antilles subduction zone shows the subducting slab at depth. We can see that the Amazonian craton is progressively thickening to the south, and those yellow bars show the seismic anisotropy observed at depth within the mantle. So the seismic anisotropy orientation can be used to observe mantle flow direction. Okay, I'll be referring to this figure in successive slides. So some key takeaways that will present towards the end is that subduction can cause lithospheric removal by directing mantle flow along the craton margin. And using 3D numerical models, we show all craton shapes aid in channelization of flow. However, straight margins are the most resistant to deformation, while gradually thickening margins are less resistant to deformation. So this margin shape can contribute to progressive removal of cratonic lithosphere until a more stable vertical shape evolves. So researchers have invoked multiple mechanisms for destroying a craton, with many different body and surface forces used to account for destruction. So these range from convective removal to thermomagmatic erosion and viscous draining, basal traction, and rheological weakening. So in reference to the rheological weakening imposed here, we can see that they have a subduction zone beneath the craton. In our study, we proposed that instead of the subducting slab going beneath the craton, it is actually subducting perpendicular to the craton, so it's nearly adjacent to the craton. What's also interesting about cratons is that they come in many different shapes. So they're spread out across the globe on all the different continents, and we can see both progressive, stepped, or diagonal margins, as shown in figure A in the top right-hand corner, and also sharp margins, which are straight, which is seen in Western Canada, for example, in C in the bottom right. So inspiration for our study was drawn from the northern margin of South America. So on the right-hand side, we have the now familiar figure I mentioned on the first slide. And so we can see that mantle flow can be inferred from seismic anisotropy observations, but also from a large suite of geodynamic modeling. So in this case, I have shown a figure from Carolee Capitano, Funicello, and Facenda in 2017, which has a look at three-dimensional modeling. And in this figure here, I'm highlighting the mantle flow vorticity that comes around the edge of the craton, the slab, sorry. So we can see that as the slab subducts, it's pushing the mantle from beneath it to the front, so into the mantle wedge. And so it's this type of flow that we were interested in studying, and to try to understand how subduction, like in the Antilles subduction zone, how the slab stirring that's caused by the subducting slab can interact with the craton, so the margin of the craton. And what's interesting is that we do have this extended alignment of the seismic anisotropy in that area. So the methodology we used to answer some of these interesting questions that we had was a numerical approach. So we used the code Underworld, and we modeled an instantaneous mantle flow field and the resulting deformation using mantle, craton, and slabs. So we chose 4 different margin shapes. Up in the top right-hand corner, I've highlighted the different shapes. So in the gray, we can see we had this tiered step shape. We also, in the small dashed line, had a diagonal margin shape. And we also had 2 straight shapes. So one craton was butted up right against the slab, and another was at a distance of 300 kilometers. So we modeled our material using temperature and strain rate dependent rheology using dislocation and diffusion creep. We imposed an initial temperature field for the oceanic lithosphere, the subducting slab, and the craton, based on assumed temperatures. So in our first model, we looked at what type of flow field do we get when we're looking at only subduction. So in this case, it really highlights the vorticity of the subducting slab and how it drives the mantle flow. So the vectors here are at about, the maximum vector is 5.4 centimeters per year, but the color is the vertical velocity. So blue is negative, going down 1 centimeter per year, and red is going up 1 centimeter per year. In our next model, we wanted to have a look at what only a craton would look like. And so in this case, it really highlights the thermal edge-driven convection that occurs around the perimeter of the craton. So we've modeled here the tiered or the step margin. The velocity vectors, we've had to multiply them by 10 times. So in this case, the longest vector is equal to 0.54 centimeters per year. So you can really get an understanding of the difference in scale of the velocities driven by the subduction slab versus the thermal cooling from the craton. You can see that we have the same scale for the colors, where blue is negative vertical velocity and red is a positive vertical velocity. So in the next model, we put the two together. So it really highlights the interaction of slab stirring and the cratonic edge-driven convection. And you can see that deformation is focused within a channel between the two. So as the mantle flows from beneath the slab around to the mantle wedge, it is forced to travel through a very small region. So deformation within this region is increased in the margin of the craton, and it's pinched. So from here, we modeled the slab and the craton system across the 4 different margin geometries, which I discussed previously. So we had a tiered, a diagonal, a straight proximal, so that's directly adjacent to the slab, as well as a straight distal craton. So that's at a distance of 300 kilometers from the slab. We measured the deformation, so the strain rate, along a transect, a northwest transect going from the mantle wedge through the channel and into the craton. And what we saw was that we were moving deformation inwards towards the craton, depending on the margin geometry. So channelization leads to deformation in the craton, depending on margin shape. So if we have a look at the figures that I've highlighted, the trends that I've highlighted here in the black, we can see that for the blue, the tiered craton, strain rates remain quite high until you get to the maximum thickness of the craton, similar to orange, which is the diagonal craton. So we still have deformation occurring within the cratonic material until we reach maximum thickness. However, we see a very distinct drop in the straight, both distal and proximal margin geometries. So this implies that increased strain rates extends into the craton depending on the margin shape, and that the straight vertical margins are more stable compared to progressive margin shapes. Okay, so what do these results imply? So our understanding on how cratons are affected by mantle flow induced by subducting slabs provides additional insight into their stability. So our results indicate that an increased mantle flow can lead to craton destruction occurring along the margins, moving inwards to the craton interior. But we also have to be cautious when interpreting seismic images of straight vertical cratonic margins, as they do not indicate large catastrophic events, or they do not necessarily indicate large cratonic events. Thanks for listening. If you'd like to see some further information, have a look at our paper. I just have a quick last slide about what inspires me, and it's our people, and so my research team here. We're all women, but we're not particularly diverse. Thank you.